Fine. So, should we start now? Yeah, fine. So this is today I'm going to introduce a topic like what is maximum likelihood and what is maximum a priori map and MLE estimation. Today I will introduce what they are and how we can interpret them, how we can use them with a very basic example so that most of you, like everybody can understand. And when I will use these things in my further lectures, so you can get very easily what I'm talking about. So this is probabilistic view of function. As in my last class, what I was saying that our what we used to what we were predicting was a function, right? What we were predicting was a function. Here is a x and this is y. And for an example, I have given some data points. So with the help of these data points, I was predicting like what could be my optimal function that will be very near to the true function, which I don't know what it is. So our task is that we have given us some data set, and using the data set, we are predicting the function which could generate them. So we can more generally learn probabilistic functions with uncertain outcomes. So what I was last class, what we were saying that, for an example, if we come up with some function, we would able to predict that value by the given x. But every time as you can see, if this is a function, so if this is a function and I want to predict it, by using the given data, it may be possible that it would have some error in it at the time of prediction. So how can I capture that error in terms of uncertainty? So the second form that rather than using this form, if I would use this form, like what could be the probability of my target function or target value by given x. For an example, if somebody is giving me this value of x and I want to predict the value, what is the value of y. So rather than giving exact point somewhere I will give some probability distribution. For an example, that probability distribution could be like this if this is a Gaussian. So rather than predicting the exact value of y, I would predict what could be the probability of y. For an example, for this given x, the probability that this will take this value is this, and if the probability is high here. So without confusing you too much, I would say that rather than predicting exact value, we would predict what would be the value in terms of probability. So there are two most common approaches that we used to estimate P of y given x. I hope that everyone understand what is P y given x, right? So here x is a vector that could be given, here x is an input and we are predicting y, as I told in last class. So this MLE is maximum likelihood estimation, and this map is a maximum a priori estimation. I will introduce it in my next slides. For that, let's first अच्छा ये पेन ठीक नहीं चल रहा है जरा boot कर देना। Okay, am I audible now? Oh, okay. So, yeah, we were discussing what is a joint probability distribution. So let's understand it with the help of example first. So I have a given, let's say there is a x, there is a x which have two components, that is x1 and x2, and let's say there is some label also which could be a binary that is having two values, true and false. So all these variables, whether it's y or in terms of x, all are binary. So I have x that is having two components, x1 and x2, and my label is, let's say, y, that is also binary, which will take true or false. So if this data is given and somebody will ask me, well, what could be the, if I want to estimate what is the joint probability distribution for this given data set, then there is a very simple trick. What I can do, I just see how many times each row is appeared in the given data set. For an example, this FF. So I will just see this row FF, and this is another, this will this FF is again an, and then this is again the third row. So there are three rows in this data set, and the total number of rows are 8. So that joint probability that x1 and x2 will be f in a given data set, the estimation I can could be estimated by like the total number, the total number when x1 and x2 appear with the total given rows. So how many time x1 and x2 appears with the total number of rows. So here f is 3 by 8. Likewise, if I will take this f2 f and t, so this is f and t. Again, this is another f and t. So there are two f and t. So this row appeared twice. So it means that x1 equals to f and x2 equals to t. The probability, estimated probability using this data set is equals to 2 by 8, because x1, when the value of x1 equals to f and the value of x2 equals to true, appeared twice in a given data set. So this is how we estimate the joint probability distribution. So likewise, and moreover, because we are normalizing it by the by the total number of rows, which are 8, so the sum of all these probabilities will definitely be 1. So if this sum is equals to 1, then I can then my definition of distribution is satisfied. Okay. So this is the, yeah, this could be a error in this is could be a minor mistake, but you got the precise idea what I'm saying. You have to count the number of times the rows appeared in a data set, and you will divide the number, that row, by the total number of rows appeared in it. That, yeah, this is a mistake. Sorry for that. You can correct it, but I hope you got the idea what it is. So when I will correct this thing, when I, for an example, if TT is appearing 2 by 8, so 3 plus 5, 6, 7, 8, right? I think now it will be 1, obviously. 3, 4, 5, 6, 7, 8. Yeah, definitely it will be a 1. So this is 2, not 1. Thanks for correction. So there is another data set that I have used here to just for that as an example. For an example, what I want to mention here that it is because the binary when in my previous table I have taken the binary case. So it may be possible that the input parameters, for an example, if this will be x1, this will be x2, and this will be x3. So here my x1 will be male and female, which is again a binary. X2 could my X2 is hours of working. What this data set is doing, it is trying to it is estimating it is showing the joint probability distribution when a male, for an example, in my first row, it is saying if the gender is female and she worked less than 40.5 hours per week and she is poor, the probability of finding this kind of combination in the whole population is this. So if and obviously, for an example, if I take this last row, the probability if the gender is male and if he works more than 40.5 hours there and he is rich, the probability of finding this kind of combination is 0.105. So this is again the case of binary where there are three variables and each you can have a binary combination. So in case of gender, it can take two values, male and female. In case of hours worked, so it could be a real value also, but just for this case of simplification, in this table it is we discretized it on the by using if it is greater than 40.5 or less than 40.5, and again by using this trick we can convert this real value function into a binary function. The third one is the wealth. So yeah, because it is a joint probability distribution always say that the sum of all these probabilities must be 1, must be 1. So now the question is, if there are n binary variables in the number, how many number of rows could be there in a table if there are n binary variables? So the question is, I have n binary variables that could be x1, x2 up to xn. So how many, yeah. So how many variables are, how many rows could be there? So this is a very straightforward answer. And because each variable can take two values and there are two n variables, so the answer is 2 to the power n. So the answer is 2 to the power n. And if n equals to 100, then obviously it is 2 to the power 100. And if I simplify it, it will be 2 to the power 10 into 10. 2 to the power 10 can be approximated to the 10 to the power 3. And this will be 10. So this will be 10 to the power 30. So there could be, if there are n if the number binary variables are 100, so the total number of rows would be 10 to the power 30, which is greater than the number of people on earth, which are 10 to the power 10. So what I mean to say, what I'm trying to emphasize here, that in the previous case, if I give you a data set like this, and for each combination you will be trying to find out you will be find out what is the count of each combination. For an example, for ff, this appeared first time, this appeared second time, this appeared third time. So to find out, to estimate the joint probability distribution, you will count how many times it appeared in the table, and the number of time it appeared, you will divide that number by the total number of rows, right? It means that to estimate this probability very correctly, you should have you should have that proportionately to the true distribution. But uh, if I have if I have binary variables that are 100, so the total number will be 10 to the power 30. And for an example, if each row correspond to each person, for an example, each row correspond to each person, like this in previous case. So this is my first person. This is female. She is female. She worked this less than 48 and she's poor. So I could have a huge data set in which there are this number of there are 50,000 rows are there, and in these 50,000 rows there is first female that will work less than 40 hours and she is poor. Again there is a second row which less than 40 hours and she is poor. Again there is some row which is same like this. So to estimate this probability of first row, how I can come up with this number 0.2531, I can count these number of rows, how many times they appeared in a total data set. For an example, my number of rows would be 10,000, so it would be around 2,500. 2,500. So this combination would appear 2,500 times in a row if the total number of rows would be 10,000. Now, what I am trying to say here, because there are only 10 to the power 10 people in this world, let's say, and because my number binary variables are 100 here, so the total number of rows will be 10 to the power 30 here, right? And because each row correspond to each person, so it means that 10 to the power 20 rows would be approximately saying 0 probability here. And 10 to the power 10 rows would have some number in it, and it may appear like somewhere in that row. So we can see that in this case, this row is to most of the time is empty. So to successfully address the issue of learning probabilities from available training data, we must have some smarter way to estimate the probability and to estimate the joint probability distribution. We will see like what I mean to say this and how we will do that in this case. So there are two intuitive algorithm to estimate a probability, that is MLE, maximum likelihood estimation, and MAP, maximum a priori estimation. To understand these two, let's take again an example so that you can understand it very clearly. Uh, let X be a binary random variable which represent a coin, and so here I am taking an example of a coin flip. So if I have a coin, it could be head and it could be tail. To represent it mathematically, I will represent this number by a random variable X. So random variable is a variable that can take any value randomly. So we are not sure what the value it will take, but the value will be decided. So it can in this case, for an example of coin, it can take either head or tail. So to represent it mathematically, I will represent head by 1 and tail by 0. So now I have a random variable that can take value 1 and 0. So 1 if it is head and 0 if it is tail. If I am saying that X is a random variable, then definitely it will have a probability distribution also, like by what probability it will take that particular value. For an example, if my coin is not biased, and it mean to that in that case the value the in that case that the probability that X will take 1 will be 0.5 if the coin is not biased. But if I say that the coin is biased, for an example, it's 70% of the time 70% of the time when I flip the coin, head appears. So in that case, the probability that X will take a 1 value is equals to 0.7 if it is biased coin. So if it is biased coin. Biased coin means there is a question from Vandana. What is biased coin? Biased coin means, for an example, if in your childhood you must have played a game like tossing with your slippers, right? With your bathroom sleeper, and it would, the probability that it would get to the right side is higher rather than it to go to it appears from the downside, because of that curvature, because of that structure. So bias means when when the probability means when the chances of appearing one, in case of binary, when the chances of appearing one value is more than the other value. So in that case this is there. So now when I'm saying this is a binary variable, it will have a distribution. So if I want to plot this distribution, so the distribution for x equals to, in case of biased coin, this is zero point 0.7. For example, this is 0.7 value and this is 0.3 value on y scale. So this value is for 0 and this value is for 1. I can show it by the distribution, and the sum of these two probabilities equals to 1. That's why it's a distribution. Okay. I will take these questions later in this, after, when I will have 15 minutes left, so that we can talk precisely. I will take your problems. So right now you can ask the questions on this, what I am currently teaching. So so let's take an example. I'll read it for you. Let x be a binary random variable which represent a coin in which x equals to 1 if it's head and x equals to 0 if it's tails. Task is to estimate the probability. Let's say task is to estimate the probability. What? So I just told you what does this mean. For an example here, theta is my probability which I don't know. Theta is that probability which I don't know. In case of biased coin, theta is equals to 0.5. So, but I want to estimate this theta by the help of a given data. I don't know what is theta. Somebody comes and gives me some data, and he said that this is a scenario that I flipped a coin, and this many number of times I have seen heads, and this number of times I have seen tails. Can you please tell me what is the probability? What is the theta here? Theta is a parameter. So what is a parameter? So in this case, particularly in this example, my theta is, what is the probability that x will take the value 1? It means how many times that the head appears when I toss a coin, right? So this is a true probability. This is a true probability of a coin. But when I want to estimate it, let's say this is, so this is theta bar or theta hat. So this is my estimated probability from the data, which could be near to or equal to, actual theta, or which could be not equal to theta. It depends upon the estimation. So that's why I am mentioning it by using this hat. So theta hat is the probability which I am estimating from the data, and this theta is the actual probability. Right? So now let's say that I have a given data. I flipped the coin n times, and for example, in case of 4 or 5 times head, first time I see heads, then tails, heads, tails, tails. So I have flipped the coin 5 times. Somebody came and tell me that see, this is the data. Can you please estimate the probability for me? So when I will estimate the probability, and for an example, this data is generated by a fair coin. In fair coin means that the probability is equal for both both heads and tails. So now if I want to estimate this probability using this data, what I will just count the number of heads, and I will denote it by alpha 1, and count the number of tails by alpha 0, and therefore my total number of count will be alpha 1 plus alpha 0. Now the estimated probability, which we have already seen in that joint probability distribution case. So the estimated probability would be very easily how many times, for an example, this would be the case head, tail, and tail. So how many times head appears in the table, right? So let's say this is a table. So head appears twice time. Total number of rows in this table is 1, 2, 3, 4, 5. So this is 2 by 5. So my estimated probability will be 2 by 5 in this case. Now, if let's say I flip the coin 50 times and I get 24 heads out of 50 coins, and let's say this case in this case this coin is fair, right? So when I flip the coin 50 times, I got 24 time heads and let's say 26 time tails. So the estimated probability will be 0.48, which is very near or very close to my true probability. In this case, I assume that I have used the fair coin to flip the coin 50 times, right? So by given data, I estimated some probability that is 0.48, which is very close to 0.5. So in general, if the number of counts is very large, for an example, I flip the coin 10,000 times or 20,000 times, and the number of flips goes to infinity, then the frequentist approach of probability says that it will approach to the true probability. So in this case, because my number of coins, number of flips is quite decent, so the probability is very close to my true probability. So it seems very reasonable and intuitive approach. But what if I have only but what if I flip the coin 3 times and let's say the coin is fair? So because this is just a 3 time, obviously either it could be 3 times heads or it could be 3 times tails or like there could be 8 different combination. But the odd probability that I will get head is let's say 1. So the total probability in this case is 0.33. So because my number of flips is very less in this case, so the estimated probability is very far from the true probability. So this approach has some limitation. That limitation is that if I will have a less data, then I cannot estimate my probability. So in my notation, I am really sorry for this PPT. This theta is a hat here. Every time you see double dots, it is a hat here. So this estimation, this approach is having some limitation, and that limitation is that if the number of the data is less, then the estimated probability is not close to a true probability. But let's say if we have some prior knowledge about that coin, somebody come and tell me that this see, there are a lot of questions appearing like, sir, this is map or MLE. Let me go through these PPT and I will take these questions thoroughly. But please try to focus on the points what I'm trying to mention here. If you're thinking other than this, then you miss the point what I'm trying to tell here. I'm taking a very basic example, and I gradually and slowly go to the point what I'm trying to mention, what I'm trying to prove. So just focus on what I'm saying here. Don't think other than that what is ML India. I will take your questions after that. So in that case, if what I was saying that if my data is quite large, then this approach will give me a the estimated probability that is close to a true probability. But if the data is less, then my estimated probability is not close to the true probability. Let's say somebody come and tell me that The coin that you have used or that we have used to generate the data was made by government. It was a government minted coin. Now, as we generally know, or whatever, because of our experience, lifetime experience, we have seen that the coins are quite fair, and the probability is very close. Probability is 0.5 for both head and tail, right? So if somebody come and tell me that this is a government coin, the government made this coin, and once he said this, that this is a made coin, government made this coin, I have, because of my prior knowledge of life or experience, I have seen many coins made by government and they were quite fair. They were fair. So my prior estimate of probability is 0.5. How can I use this prior knowledge in estimating my new probabilities? Is there any way that can I use this prior information or prior knowledge while having some data? For an example, this is my data: head, tail, and tail. So this is the data. I have prior knowledge that this coin is a government coin, and because this is a government coin, the probability is 0.5, which I know. I'm not sure, but because I have some prior knowledge. So I have two informations now, the data and the prior knowledge. Can I use this prior knowledge and data to estimate my probability now? And will this prior information will help me to estimate my true probability? Let's see that. So what I say, because somebody come and say that, oh, yeah, this is a government made coin, and the probability is very high that this is a fair coin. So as you said, this is a fair coin. I will imagine that I will visualize, or I will visualize in my mind that if I would have tossed this coin 100 times, so out of 100, 50 would be heads and 50 would be tails. So I will imagine some number in my head, and let's say if in case of government or fair coin, I would imagine that there is alpha 1 times head appears and alpha 0 times tails appear, right? If alpha 1 time head appears and alpha 0 time tail appears, this is my prior belief of that head. In that case, let's say it is 50-50. If it is there, if I visualize or if I imagine there are 100, if I would have flipped the coin 100 times, then 50 would appear head and 50 times tail would appear. This is what I imagined. Now somebody come to me and tell me that this is head, tail, and tail. This is the data. What I can do, I will say this head appeared 1 time in my data set. I will add my this imaginary data set or imaginary value regarding heads to this 50. I divide it by 1 plus 50. This is head appeared in a data set. 50 is my imaginary number, that is alpha 1. How many times tail appears in my data set? It is 2. And how many times my imaginary data set, how many times tail appeared in my imaginary data set? That is again 50. Right. Now I will calculate this probability. This is 51. Divide by 103, I think. 103. Now if I will try to calculate it, it will be, I think, more probably 0.48 or 49. I don't know. Let's see what it will be. So it will be more close. The point is that it would be more closer to 0.5. But in that previous case, it was only 0.3 when we didn't have any prior knowledge. So we used some prior knowledge, which may correct or which may not be correct. don't I will address this point like this prior knowledge which may be correct or which may not be correct in my future slides. But for now, let's say so I am trying in this slide, I am trying to tell that how can I use my prior knowledge with my data set. So this is one way that I can estimate my probability, and in that probability I will add my data with the imaginary data set and the total number of times. So here you can see this alpha 1 plus alpha 0 equals to n. That is my total number of times in data, like total number of rows in a table in my data set. And this is total number of rows, gamma 1 plus gamma 0 equals to, let's say, n, an imaginary n gamma. So this is that imaginary data set which I produced or I visualized by my prior knowledge, and this is the data set which I have in my data set. Using these both information, I can estimate this probability like this. In this slide, does anybody have any question? Okay, fine. I think this is quite clear. Nishta is asking, first tell me whether you can see this, because I have shared my screen. I hope that everybody can see this chat window here. Is it? Okay, fine. So every time I will address it, I will try to, every time I will address the question, I will highlight that question. So Nishta is asking, sir, okay, but we cannot send to, I don't know. So this is, sir, is imaginary data set as prior, same as prior. Yes, I already told 100, like I repeated it more than 10 times that I am using my prior knowledge to generate that imaginary data set. So if I am using my prior knowledge, so obviously this imaginary data set is, I visualize it using my prior knowledge, right? It is what I'm using it. So second algorithm has several iterative points. It I will read it one by one. It is easy to incorporate our prior assumption about the value theta by adjusting the ratio gamma 0 and gamma 1. In this point, what I mean to say, for an example, if that coin, somebody told me that it was a government minted coin, it means would have to adjust my gamma 1 and gamma 0 such that the probability of gamma 1 would be 0.5, because it was a government minted coin. So how can I take the values? I could have take the value, as I told in my previous slide, that I could take the value 50 for gamma 1 and 50 for gamma 0. In this case, if I will calculate the value of probability that 1 will appear in my imaginary data set equals to 0.5. So I adjusted this ratio such that this would be 0.5. If other than that, for an example, somebody come and ask me, no, it's not, it is not a fair coin. I have seen that guy, he used that, he may have the biased coin, and in that biased coin the probability could be zero point 0.7, let's say. Then in that case, if I have some prior knowledge that this coin could be the probability could be zero point 0.7, then I will adjust my ratio by using gamma 1 equals to 7 and gamma 0 equals to 3 in case there are 10 rows in an imaginary data set. And if there are 100 rows in imaginary data set, in that case gamma 1 it will be 70 and gamma 0 will be 30. I hope that this is very clear, right? So it is easy to express our degree of certainty about our prior knowledge by adjusting the total volume of imaginary coins. Now this is what somebody tell me, or I have some prior knowledge about my data set that this is, but how strong is that? That also I can express it by gamma 1 and gamma 0. If somebody say that no, I am very 100% sure that this coin has is a biased coin, and the theta would be zero point 0.7 here, and or I am very much sure that this coin is there, yeah, this is having 0.7 probability. In that case, I strongly define my belief by increasing this number. Now in this case, I am believing that this coin, if this coin were by taking this large value, I am saying that I am very much sure that the gamma 1 is equals to 7,000 and gamma 0 equals to 30,000. But if somebody say no, I am not very much sure that the value is 0.7. If I am not very much sure, then I could have taken gamma 1 equals to only 7 and gamma 0 equals to 3. I will tell you why, how it will affect the final thing. But most of you, if you can visualize mathematically, it's a very easy thing. What actually is, okay, I will let you know in the next slide or right now. So what actually happening, because this is alpha 1 plus gamma 1, alpha 1 plus gamma 1 plus alpha 0 plus gamma 0, right? Now, if these values are very high, gamma 1 and gamma 0, my data set will have less effect on the ratio, because this gamma 1 is and gamma 1 and gamma 0 is a very big number. They are very big number. So for an example, this is 50, gamma 1 and gamma 0 is also 50. So 50 plus 100 is already there, right? Because of this gamma 1 plus gamma 0 equals to 100 and gamma 1 equals to 50. This is already there. This is a very big ratio. And I'm just adding my minor small data set with it. Let's say 1 plus 2. That is, this is my new data set and this is my imaginary data set. So this addition will have a very less effect on it. Now, if I was less sure about my certainty, then it could be only 5 upon 10. And as I will generate the data, by my coin, and let's say the coin was biased. The coin was biased and I flipped the coin 500, let's say 100 times. And my coin was biased and I am assuming the bias probability was 70. So in my new data set which I generated, 70 times head will appear out of 100 times, right? And this was my prior knowledge, 5 by 10. So this 70 by 100 will dominate my prior knowledge with the data. But if I would have very strong, so here I'm saying that as you will have a very large data set, the effect of this prior will be diminishing, right? So second algorithm is a special case of first algorithm, because I don't know what is my prior belief, and I am putting alpha 1 and alpha 0 equals to 0. So last point, as I observed, data grows towards infinity, the influence of imaginary data goes to 0. Okay, so I will take some questions now. How to come up with prior sample? So I already told you that this is it depends upon the knowledge. It depends upon my prior knowledge. For an example, in case of government coin, I know that this is a government coin, so the probability that the gamma 1 will be 50% head and 50% tails. Okay, so in one by one, in which case we are increasing gamma from 7 to say 70,000. So in that case, if I am increasing the gamma from 7 to 70,000, it means that I am less trusting my data rather than my prior belief. Sorry, I will say it again. It means when I am using very large values for gamma, it means I am strongly believe my prior knowledge rather than data. And let's say the data is, and to overcome this knowledge, prior knowledge, for example, I use 70,000. It means the total data set I imagine 1 lakh, right? Out of 1 lakh coin flip coins, there are 70,000 time I assume there would be head. Now when I flip my coin, let's say 20 lakhs or 30 lakhs times in the multiple of 1 lakh, and if the coin was really fair, now this ratio, this prior knowledge will have less effect in my recent knowledge. So I will show you some examples then. So we have only prior knowledge and present experiment. Based on the ratio, either prior knowledge can dominate or present experiment can dominate, right? Right, sir. That's what I said. Okay, I'll take some more questions also. How to consider imaginary data set if we have high data set? How to come up? So there are a lot of questions regarding prior, and I will address these questions again in my future slides. So estimating probabilities. Now I will relate these two approaches with what is MLE and what is MAP. So both algorithms exemplify, means illustrate, the two most widely used approaches to machine learning of probabilistic models from training data. Algorithm 1 follows a principle called maximum likelihood estimation, in which we seek an estimate of theta that maximize the probability of observed data. I will clear this statement what it is. So here what I am trying to say, that I am trying to find out my theta, and that theta I will try to find out theta in such a manner that the probability of generating the data is maximum using that theta. I will explain this with the help of example. So algorithm 2 follows a different principle called maximum a posteriori estimation, in which we seek the estimate of theta that is most probable given the observed data plus background assumption what about its value. It's nothing but the same. Formally I am describing or writing the same thing what I was just discussing in the previous slides. Okay, so these are some examples. So there are some examples, and I think I should pause. Pause that.